So, welcome to this module of chemical process calculation, which is going to be on energy balance without chemical reaction. So, let us see what are the things we are going to talk about. So, when we are talking about energy balance, the first thing we need to worry about is energy balance of what? And you all know the answer. It is the energy balance of a system. So, this is actually the point where you should highlight the different types of system, the concept of different type of system to your students, which are isolated system, closed system and open system. Now, we are talking about energy balance. So, the governing equation in this particular case is the energy conservation equation, or the so called first law of thermodynamics, which actually tells us that the total energy of a system and its surrounding combined together remains constant. So, of course, only thing, it is a good point to highlight to your students that only nuclear reactions cannot be covered by this conservation equation, and then from here, depending on what type of system you have, you can have different forms of the conservation equation. For example, if we define E, use symbol E to be the total energy of a system, then for an isolated system, of course, E is constant, because we know that it does not exchange mass or energy with the surrounding. So, let us focus more on the energy balance of a closed system, where exchange of mass is not allowed with the surrounding, but exchange of energy is allowed. And then comes the immediate question that what are the modes by which energy can be exchanged between the system and the surrounding. And of course, there are two modes available through which it is possible, which are work and heat transfer. In order to highlight or teach these topics well, it is better that at this point of time you sort of introduce some of the critical pedagogic terms like boundary. Please do highlight that the nature of the boundary is extremely important in defining the nature of the system, because see, if the boundary is pervious or it is porous, then it actually becomes an open system. If the boundary is sort of impervious, but it can sort of expand or it can allow transfer of heat, or it is not insulated, then it is a closed system. And if the boundary is insulated as well as it cannot move, it is rigid, then that forms an isolated system. So, just from the definition of the type of the boundaries, one can very nicely correlate the type of systems. So, we already talked about the closed system and open system, etc. This is also an important area, a good point, a good time to highlight the properties of what is the difference between intensive property versus extensive property and maybe it is equally important to define the difference between state function and path function. You can probably also, if you want, give students, because these are going to be, this is the chemical engineering 101 subject. So, it is good to tell to them what is equilibrium, what is steady state, what is unsteady state, so on and so forth. And they will also be knowing about different type of processes. So, you can also highlight what is a process. So, process is a sequence of steps by which a system sort of transfers from one equilibrium state to another equilibrium state. And you can also, of course, your thermodynamics teacher subsequently will tell about all this, but it is not a bad idea to highlight about the equilibrium process and non-equilibrium process. But let us not get too much into that, but you can probably at this point of time talk about different type of systems that are possible from the standpoint of the nature of the work and heat, like adiabatic system, isothermal system, Please do understand that these are very simple terms for us, but for the students they are learning it for the first time. So, it is important you highlight each one of them: isobaric system, isochoric system as a good reference. So, of course, we know this is Q is equal to 0, isothermal system delta T is equal to 0, isobaric system delta P is equal to 0, and isochoric system there is no change in volume. And so, once you have defined the state function, path function, or the state variable, path variable, you are now in a position to sort of take up the first law of thermodynamics in its mathematical form. So, let us do it for a closed unsteady system, and if you just extend the basic statement of the first law of thermodynamics, what you get to know is the change in the energy of the system. So, E I am designating as the energy of the system. This is sort of the summation of work done and heat that is transferred. I am deliberately using the plus minus sign just not to worry about whether work is done on the system or work is done by the system or heat is transferred to the system or out of the system. You can just carry it and tell the students to sort of consider things appropriately. The convention that we will follow is, if work is done by the system, it is negative work, and the reason for that is you must highlight that there is no assumption or anything like that. When system is doing work, it is actually spending its own internal energy. So, there is a reduction of its own internal energy, and therefore, this is conventionally considered to be as negative work. In contrast, if work is done on the system or if heat is transferred to the system, the internal energy of the system goes up, and therefore, we consider that to be positive. Now, once we understand or agree to this, so in the differential form, this will look something like this, and this is a good point for you to highlight the difference between exact differential and inexact differential. So, please do care to write that dE is an exact differential, because it is talking about you can integrate it between the state 1 and state 2, and there are going to be the energy levels associated with the initial state and the final state, while Q and W at initial state or at the final state there is no Q or no W. So, this is only energy in transition. So, it is only when there is a process there can be heat transfer or work done, that is work that is done. So, this is a good point to highlight how path functions sort of correlate with inexact differentials. Understanding all this, you should next move on to what are the different components of each of these terms. As far as energy is concerned, the different components are kinetic energy, potential energy, and the internal energy of the system. Of course, you can give a first level idea that even the internal energy can or sort of comprises of internal potential energy, the so called van der Waals interaction or the interaction, intermolecular interaction, internal kinetic energy, and there can also be contributions from rotation and vibration, which are of course small, and for monoatomic gases or ideal gases they are often neglected. In fact, that is actually how you lead to the definition of Stokes fluid. Let us not get into all that and overcomplicate things, but what I will really appreciate if you highlight to the students at this point of time that kinetic energy of the system is typically half mv square what they write, but internal kinetic energy is the kb into T, because I have seen many students confuse these two things. So, this needs to be clearly highlighted that what are the different components. So, if you now start to talk about the different components of Q, you can have classifications based on the mode of heat transfer, and which we all know can be our conduction, convection and radiation. And of course, in chemical process calculation we do not teach about them, we just tell them that you will be taught in details about these things in your heat transfer lessons. Similarly, when it comes to work, again you can have many types of works like mechanical work, electrical work, shaft work. Even for a flowing system you can have what is so called the flow work. But now I think this is a good point to highlight to the students that as chemical engineers what type of system we are going to look into. So, we are going to look into, let us say, a reactor vessel or a tank or a heating vessel or something like that. So, I will not emphasize a reactor right at this moment, because if you have a chemical reaction your problem becomes more complicated, because you talk about energy balance with chemical reaction, which we are not talking in this particular module. You should sort of introduce the concept of energy balance without a chemical reaction. So, what is going to happen? See, nobody is going to place this reactor on a fast moving vehicle, for example. There are very, very few examples where a reactor is moving around, or you are not going to run away with your reactor from let us say the plains to some place in Himalayas. So, the question of you can make it interesting to the students like this, and you can tell that the issues, though we know that energy, total energy comprises of potential energy and kinetic energy, for a system like this the energy change actually boils down to the change in the internal energy only. So, it is mostly the change in U. So, for many practical cases dE tantamounts to change in du. This is how it comes from very, very simple physical consideration. Of course, again question is for this type of a system, maximum if you have a piston or let us say an engine or something like that, maximum you can have some mechanical work and nothing else. You are not likely to do any electrical work, and we typically do not focus too much about on shaft work or flow work. For a flow is not possible for a closed system. Therefore, these can be eliminated, and therefore, the only work element, if at all we worry, is about the mechanical work, and which we all know in that case, if you consider only mechanical work, your expression for W or dW becomes PdV. It can be related only to this much. So, these are also interesting points where you can actually highlight the critical importance or the difference between internal energy and enthalpy of a system, because one can simply talk of a very simple system where it is a sort of a frictionless piston on top of a vessel or something like that, and it receives some heat from outside. So, you know what is going to happen, its temperature is going to go up, and as a consequence its volume is going to expand. So, question to ask is whether such type of a system is better explained in terms of internal energy or enthalpy. The reality is two things are going to happen because of this transfer of heat. Part of the volume is going to go up, and in the way the system is going to do some work. So, you have a PdV component, and you also there is an increase in temperature which actually raises the internal energy. So, it is better the heat that you the way to place about it is the heat you are supplying is sort of consumed in increasing the temperature and the internal energy of the system, and simultaneously creating some more space where the molecules now at a higher temperature can roam around freely. So, these are the situations or where the volume is not preserved. We all talk about that, where the volume is not preserved, enthalpy is a better indicator for such a system. So, with this much of knowledge, what you now need to emphasize that what are the likely consequences if you heat up or there is an energy balance for a system like that. And the likely consequences are very simple. The system can get heated up or cooled down depending on the size of the Q, or again if you are performing some work based on that, or on the system, or some work is done by the system. So, there can be a change in temperature. This is the bottom line. It is very simple actually. So, if there is a change in temperature for a system, what is going to happen? So, of course, if the temperature changes, the system can either get heated up or it can get cooled down, but there can be additional things like it can also change its phase or change its state. Like if you have, let us say, some water in a tank, it is a very simple example you prefer to give, and you supply or go on heating it from outside. First the temperature will rise, and then once the temperature is adequately heated, it reaches its saturation temperature, the boiling point, it then undergoes a phase transition to steam. So, what exactly the calculations that we require to do? We require to actually find out that depending on a particular amount of work done, which is rare, but heat that is transferred, which is more common for such systems, how the system gets heated up or cooled down. Bottom line is, to calculate this you actually need 5 parameters, and they are, they are the specific heats, in the solid phase, in the liquid phase, and in the gaseous phase, and the latent heats of fusion, boiling, and reverse. So, at this point it is important to highlight to your students that, see, these calculations you have been doing for a long time from your high school days, but the thing is that all the Cp values and lambda values were provided to you. And as engineers, one of the challenges that you have to face is that you now look into a new system where these values are not available and you do not have all the data available, or you have a new compound and something like that. So, it is extremely important that this is an engineering course, this is not a science course. Therefore, you must highlight to them that as engineers it is extremely important to have a gross guess of something better than nothing. So, next what we actually talk about, whichever textbook you follow, and in the handout everything will be given, predominantly my discussion is in the lines of a very popular textbook, that is Himmelblau's textbook. We actually will spend some time in exploring, first defining the specific heat, because that is important, that determines determines how much a system is going to be heated up or cooled down or whatever, and subsequently if we can estimate some of these based on whatever physical principles we have. So, first thing is, please refer to the handout for the detailed definition, which I am not going to discuss here, but what exactly is the specific heat? And it turns out that so first thing we need to talk about is the heat capacity, right. So, heat capacity is the amount of heat required to increase the temperature of a body by 1 degree. So, it can be this is what is the definition of heat capacity. In fact, many of you will say that specific heat is nothing but specific heat capacity. So, what is the heat required per unit gram or something like that? Please do care, I mean you can highlight to this to your students, or at least you get very clear. The specific heat is not defined like that. Specific heat, just like specific volume or something like that, or specific gravity, is actually dimensionless. So, specific heat is nothing but it is the ratio of the heat capacity of a body to the heat capacity of equal mass of water. But somehow we prefer to write Cp as the specific heat as the heat required to raise the temperature of an object by a unit weight of an object or unit mole of an object by 1 degree. So, kindly clarify this, because just the way specific gravity does not have unit, we always write an unit to specific heat. So, that is not exactly fully correct. So, these things should be highlighted and people will sort of feel very excited to know the nitty-gritty details, where at certain places what is used very commonly has actually some anomaly and things like that. So, heat capacity of any quantity of a substance can be expressed like this. I think you can refer to the handout, but it is self-explanatory. Q transferred, delta T is the temperature rise, mass m is the total mass. Now, what we have learnt already from the conservation equation is dq is du du plus dw, and which for the type of systems we are talking about, this transforms to du plus pdv. Now, so from this expression we can write dq dt is equal to and when we evaluate, we all know that when we evaluate dq dt at constant volume and for a unit mass, then that is nothing but Cv, and which you can show from here clearly, because since V is constant, therefore, in this expression pdv is going to be 0, and therefore, it tantamounts to du dt at constant volume, or you can write it to be du dot dt. So, of course, this 1 by m is there. Please refer to the handout for all these critical details. Now, what is Cp? In that case, I will use this particular space over here. So, Cp is nothing but dq dt evaluated, or maybe I will use a new page. So, Cp is dq dt evaluated at a constant pressure, right. And the important formula we need to remember is at constant pressure, and this in fact you can write this now as u plus pv. So, look carefully what we have done. We have actually written pdv as delta pv, and this is possible only when pressure is equal to constant. So, please do highlight these things, because people do not understand and they do random thing, and u plus pv, as we have already talked about, is nothing but dh dt, right. So, this is how you can sort of get the definition of Cp and Cv. Now, many of us know that for ideal gases this relation is valid, and we also have this working at many of the places. So, you can get this Cv is 3 by 2 r from kinetic theory of gases. Please refer to the handout, you can just correlate it to this relation of pressure you have from the kinetic theory of gases, and I am not going into the symbol. So, this we can write in terms of it tantamounts to n into ut. This is a translational energy of a possessed by a mole of gas, and by knowing that PV equal to nRT, we actually get PV equal to 2 by 3 NUT. This is what you can correlate from here. Again, every detail will be there, and what we can write is that 2 by 3 NUT is equal to nRT, and therefore, what we get under the assumption that the translational kinetic energy is the total energy of the system is U equal to 3 by 2 RT. I had to rush because time is very, very short. I do not want to spend too much amount of time, but you have an expression of U now, which you sort of, if you just plug into this expression based on the fact that U now you have 3 by 2 RT, then du dt will be 3 by 2 R. So, this is important because based on this you can get a first approximation for the CV values of gas, and then you can similarly get an expression for Cp, which turns out for ideal gases is equal to 5 by 2 R. Because why we are doing all this? Because as I mentioned, in order to calculate the total thermal effects, we need to know the sensible heat and the latent heats. So, of course, there can be other relations available. Cp for an ideal gas mixture you may highlight, it is a weighted average, weighted sum of it. Then comes the, so we have done with the heat capacity of gas. Next we worry about, this is done, of solid and liquid. Kindly introduce the students to the concept of the Petit and Dulong law. Please refer to the handout for the details, which says that the heat capacity of all crystalline solid elements is nearly constant and it is equal to 6.2 calorie per gram atom. In fact, if you gram atom Kelvin, if you look at this number 6.2 calories, it turns out to be 3 R. So, for a gas it was 3 by 2 R, here it is actually 3 R. This rule works well for elements with atomic weight higher than 40. There are tables available, all the details are there in the handout, what are the values for elements with lower atomic weight. This is for elements, so this worked for elements, as they say crystalline elements of course. So, you can, in fact you should at this point worry about what happens to the compounds. So, for that we have what is known as the Kopp rule. The heat capacity of a solid compound is approximately equal to the sum of the heat capacity of the constituent elements. So, you can very well use the Petit Dulong law, along with the exceptions. There are certain numbers like heat capacity at 20 degree for carbon is 1.8, hydrogen is 2.3 and so on, which are not 6.2. Right. So, all these details I have provided in the handout, which you can refer to, and you can calculate the Cp of solid compounds. Similarly, Kopp rule can also be applied for liquids, where all the values are, again I am providing in the handout. Typically for a liquid it says that the value is 8.0 and there are certain exceptions, but so based on this Petit Dulong law and the Kopp rule, now we have actually this in our disposal, which is a major step. Of course, this comes directly from the kinetic theory of gases. Sorry, I wrote vapor instead of gas. In fact, you can sort of emphasize to your students in the class, they will be very appreciative what is the difference between a vapor and a gas, and do care to talk about it from the standpoint of critical point, which I am just about to come. So, typically once you are going to heat up something, what you are likely to encounter is a situation like this. So, and I guess you can all understand what it means. So, as the temperature increases, so this is the solid stage, this is now there is it's melting, and then you have the liquid, and then there is evaporation, or this is the boiling, and you have the vapor phase. So, you can calculate the delta H, and this is exactly what I am trying to impress upon you. In order to do this calculation, you actually need the 3 Cp values, which we have already done, and the 2 lambda values, right. So, let us focus some time on that, but it is also a good time to sort of highlight the generic nature of the phase diagram. Maybe again please refer to the handout, it will all be there. So, this is a typical PT type phase diagram, right. So, you must emphasize this is the triple point, and this is somewhere over here is the critical point, right. And you can also, based on this diagram, can highlight that this is not a typical phase diagram for water. For water, the slope has to be in the negative direction, and if how to come to that. So, instead of passing it as an information, ask them if they all know about regulation, which we all know, and you cannot explain regulation if the slope is positive. So, kindly talk about that. Heat of fusion, unfortunately latent heat of fusion, there are no analytical ways to sort of have a first approximation. So, you can't do that. Of course, please do also highlight that many times there are phase transitions. So, within the solid phase, like this ordered disordered transition, or martensitic transition, or ferromagnetic to paramagnetic transition, and so on, which are not very important thing, but a little bit of flavor of material science comes in. So, last thing that remains is the heat of vaporization, and please introduce the concept of the Clapeyron equation here. Right. So, I am just writing the and please do highlight this is an exact thermodynamic equation, and then we all talk about the Clausius-Clapeyron equation. So, please do highlight that the specific volume of liquid is much smaller as compared to the specific volume of gas. Therefore, one can neglect, one can consider the denominator to be T into Vg, and the moment you sort of do that, you are now in a position to. So, this equation is the Clausius equation, and when you plug in this approximation that Vg is much greater than Vl, you are talking about Clausius-Clapeyron equation, and this Vg you can correlate from an ideal gas law. So, eventually you get an expression of delta P by this P star, what is the vapor pressure, T into R T. You can. So, this is also a good point to introduce the concept of vapor pressure to the students, and then you can perform an integration to show that if you know the vapor pressure at two temperatures, based on that you can get an estimate about the delta Hv. Kindly refer to the handout for more details, and one thing I did not get the time to cover in this lecture is that in conjugation with Clausius-Clapeyron equation, you can introduce or you can talk about the Troughton rule, which tells you something like just refer to all the details. Delta Hv or by Tb, or the boiling temperature, is constant. The ratio of the molar heat of vaporization of a substance at its normal boiling point to the absolute temperature is constant, and for many material this K as a value of 21. And Troughton rule, you can sort of a modified version or a more extended version of the Troughton rule is the Christiakowski equation of nonpolar liquids, and from that you can get to the Gamson and Watson equation, and can use the reduced pressure and reduced temperature to evaluate delta Hv. All these details I am providing in the handout. So, with that I will stop my lecture on energy balance without chemical reaction, and I think I have given you a basic flavor of how to handle the conservation equation, conservation of energy, the first law of thermodynamics for a closed unsteady system. Please do also care to talk that if you have an open system, you have to use this equation in a rate form, which is you divide it by time delta t and take a limit of delta t tending to 0. So, the functional form essentially changes to something like dE dt is q dot minus or plus minus w dot or something like that, and this is actually valid. We do not handle these type of situations too often, but for a flowing system, for a continuous reactor, this type of thing is important. And then what I emphasized a lot, what you should also emphasize a lot to your students is that you need the parameters to be estimated, and we spent some time how to get the first level approximation of the specific heat capacities or the heat capacities, now that you know very well that they are different, and the latent heat of the melting and boiling. Thank you.